So in the previous video, we learned the basic idea for interval estimation. So the idea is we fix the confidence level and then obtain the margin of error, because basically underlying the derivation is the trade-off between margin of error and the confidence level. We want higher confidence level so that our estimator is more likely to be correct. On the other hand, we would like to have smaller margin of error for the estimator to be more informative. But they are trade-off, so we have to fix one of them, that is the confidence level. We fix the confidence level first, and then we find the minimizing margin of error that satisfies the confidence level. Okay? So then, like previously, we used 95% example. When you choose 95%, which is the most common choice, 95% implies like plus minus 1.96 contains 95% in the standard normal distribution. That is the key idea how we find the margin of error. And now we are going to generalize that idea to any confidence level alpha, like error probability alpha. So like alpha is the error probability we allow, and that means 1 minus alpha is the probability the interval has to contain, right? The interval contains the true parameter with probability 1 minus alpha. Okay, this is the equation we are going to solve for m, right? So m is the only unknown, what we are going to solve for in this equation. So alpha is, previously we chose alpha as 5%, but now it can be anything. The idea is the same. We are going to rearrange the inequality so that the random variable x bar is in the middle, right? And then we know the x bar sample average is approximately normal distribution by the central limit theorem. So we are going to standardize x bar in this way, subtracting mu dividing by the standard deviation, right? And like mu cancels out, and in the end we have this, right? By the way, this is particularly, the canceling out mu is important because remember, we are estimating mu. Mu is the parameter of our interest. We would like to estimate the true mean, which is mu. But if mu is not canceled out, then your margin of error must contain mu again, which is like a little bit weird because we are estimating mu itself, but it has to contain mu again. But fortunately, mu is canceled out, so we get like clean marginal error, or like without worrying about another estimation of mu. Anyhow, so we get the same inequality like after standardization, which is still 1 minus alpha probability. And then now it's to find a value from the standard normal distribution function. Right? We would like to find number a value a, such that plus minus a contains 1 minus alpha probability, which means the error probability alpha is either overestimation or underestimation. So half of alpha is put on each tail, right? So like probability greater than alpha is greater than a is alpha over 2. Probability smaller than minus a is alpha over 2, right? Right? Underestimation and like overestimation. So we are looking like they are symmetric, so we are going to use the second equation only. That means a is the top alpha over 2 probability value, right? Which was denoted as z subscript alpha over 2. We defined this notation in chapter 6. So all those practices we did in chapter 6 is to get this formula, right? So to get this point. We promised to denote it as z alpha over 2. So then we are going to equate the margin of error divided by the standard deviation equals the chosen value from the standard normal distribution, right? Which implies by moving this term to the other side and replacing unknown sigma, unknown standard deviation with its point estimator S using the sample variance formula, then you are going to get margin of error in this way. So again, this is a general form. Like you just need to plug in alpha that you choose. Like alpha could be 1%, 5%, 10% typically. So depending on what you choose, only this part changes. This is standard deviation you can calculate. Sample size is what you can calculate. So, and in the end, margin of error is here, and the point estimator x bar is also what you can calculate. So you can calculate all those numbers, and then you obtain a confidence interval for the mean with 1 minus alpha confidence level. Okay, that is how you obtain a confidence interval. Okay, let's have a look at this. There are only 4 components, even though the derivation involved several steps that we learned earlier. But in the end, the result is pretty simple, right? This is the result. And remember, you only need 4 information: sample average, and sample standard deviation, and sample size. So these 3 guys are calculated from the data, right? And finally, the z alpha over 2 value. This is how much you are going to sacrifice, or how much margin of error you have to allow, right? This depends on your choice. You just choose how much error probability you sacrifice, and then standard normal distribution will return the corresponding value. Okay, and then some observations depending on these 4. X bar, when X bar increases, margin of error does not change. It's just like parallel shift. When X bar increases without changing anything else, then margin of error is still the same, confidence level is still the same, nothing changes, only the center changes, location shift. And when standard deviation increases, then that means your data have more noise, more uncertainty, right? Therefore, you have to allow a larger margin of error. You have to expect greater errors, so you have to allow more margin for the error, right? So the interval will be larger. And when sample size increases, that means you have more information, more data, better data. So you can estimate more accurately. Your accuracy will improve. So as a result, the estimation error will be smaller. So you only need a smaller margin. So the margin of error will decrease as the sample size increases because it is in the denominator. So your estimator will be better, like more informative. The interval will be smaller. Finally, z alpha over 2 depends on the confidence level you choose. But when you choose a smaller alpha, then z will increase. The smaller alpha, the larger z alpha over 2. Because if you allow, say, very small error probability, then to cover that much area, that much probability, if you imagine the bell curve, you have to cover more probability. So then you have to have a wider, like a larger interval to cover more probability. So a smaller error probability implies larger z. So your margin of error will increase. So your interval, confidence interval, will be larger. So then each of them have different roles in the estimation, but they can be calculated. All of them can be calculated, so should be pretty straightforward. And finally, I'm going to just give you a common table. You can just use this table to find the value. So I said The common choices are confidence level 90%, 95%, 99%. Right? You choose, usually you are going to use one of them. And then error, that means error probabilities are 10%, 5%, or 1%. Okay? That means on each side, either underestimation or overestimation, each side error will be half of the error probability, 5, 2.5, or 0.5%. And then in terms of cumulative probability, you have to flip them, like taking 100 minus this one side error probability. So you have to find from the normal distribution, you have to find 95 percentile, 97.5 percentile, or 99.5 percentile. Then on Excel, like let me show you. So I will show you. So like first confidence interval, which is 90%, 0.9, and 95% or 99%. That is the confidence interval, and then error probability will be 1 minus the confidence level, confidence level. Error probability will be 1 minus the confidence levels, and then each side has its half, right? And then cumulative probability is again 1 minus the half of the error probability, right? So that is cumulative probability, and finally z alpha over 2 value can be calculated. So these are the values, z values we are going to use for the marginal error. You are going to multiply this to the standard deviations, right? And like, of course, usually we round it to say second decimal place, or depending on the textbook, may have more. But anyhow, it is approximation, and we are going to use these like second decimal place. So it's up to you. You may use Excel, or you may use just these rounded numbers. And anyhow, the rounded numbers are calculated here. So if you want to use unconventional confidence level, that is also possible. For example, if you are willing to allow 20% confidence level, like that, I mean 80% confidence level, then you only need 1.28 multiplied to the standard deviation. So this rule is a general formula, but for the typical choices, you can just go down to here. Okay, and also what you can see here is as you increase the confidence level, your margin of error must increase together, right? Right. It's that is trade-off, right? So then let's think about a more specific example for confidence interval. Like I will think about like COVID-19 treatment. So an insurance company wants to estimate the expected cost of COVID-19 treatment, right? And from a sample, the insurance company collected 100 COVID-19 patients. And based on the 100, what is observed is a sample average of $20,000, and the standard deviation was $5,000. Okay, so this is based on the sample, only 100 sample. But what we want to know is the population, every COVID-19 patient in the world, right? That is impossible, so we are going to use the 100 sample to make a guess about the population, right? We are going to use an interval estimation with 99% confidence level. The insurance company wants to have a very high level of confidence, right? So 99% is the choice. How can we do that? I'm not going to do the derivation again. We just use the formula. The final form of the confidence interval look like this, and you just plug in the numbers. Actually, pretty simple. X bar is calculated here, 20,000. Sample standard deviation was given 5,000, and sample size was 100. So square root of that is 10. You just plug that in. And what remains, so X bar clear, S clear, and clear. It only remains to calculate Z. It depends on the confidence level 99%. So you may use Excel, right? This is what you get. This is what you get from Excel, or you can just go to this table and choose this number that corresponds to 99%, and then you get 2.58, right? Following the previous logic, calculating error probability and half of the error probability and turning that to cumulative probability, blah, 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 you get 2.58. So pretty quickly, we get the margin of error. Margin of error is $1,290. So in other words, like this much standard deviation multiplied by the standard normal value, and then this is the margin of error. You have to subtract and add this number to the point estimator. Point estimator is 20,000, like based on the sample. The sample average is the best estimator for the true mean, but it can be wrong. So we allow plus minus this much. So the conclusion is, so our estimation results is the true mean will be somewhere in between $18,710 and $21,290, somewhere in between them, with probability 99%. So still it may be wrong, but the error probability is 1%. Other 99% is correct, right? That's how we use interval estimation. So it took like quite a few steps to get to the formula, but in practice, the usage is pretty simple. Okay. So it's your turn. Like now, I changed it. The data are the same. I want you to try the algebra with 90% confidence level. Try what happens when you have 90% confidence interval. So pause the video now and resume when you finish your algebra. So, okay, let me turn the page. So, same as before. The only difference is we are using 10% error probability. So 10% error probability corresponds to 1.64. So 10% error probability means each side must have 5%, and then we are looking for top 5% value or 95 percentile. That is 1.64. As you can see here, we choose 90%, and then we get this number. Okay, so this is the number we are going to use here, 1.64, and then it's super simple algebra. 1.64 times standard deviation 5,000 divided by square root n. Okay. Another thing you have to be careful here is, remember what I multiply those S here is the standard deviation you calculate from the data. So it is like single observation level standard deviation, but you divide it again by square root of n. Okay, so don't forget to divide it by square root of n, because it is standard deviation for the sample average. Okay. Anyhow, so the margin of error is now 820, which is smaller than what we get. Earlier we got a margin of error of like 1200, but it is now like say much smaller. That's because I accepted higher error probability. So your interval will be smaller, more informative than before. Okay, so your interval will look like this. Oh. So for comparison, in this numerical example, depending on the confidence level, you can see how the confidence interval changes. Lower confidence limit decreases because your interval should wide out. Um, the lower limit must be lower, even lower, and upper limit must be even higher as the confidence level increases, right? But their center is always the same. Their centers are always fixed at the sample average because that is the point estimator. Point estimator does not change. But when the confidence level changes, it's a matter of margin, how much margin you have to add, right? So the margin will increase as the confidence level increase, right? That's again the same conclusion we just learned. But so I said as if the confidence level and the small margin are trade-off, but actually there is one possible way to achieve both of them. To overcome the trade-off, what we need is sample size, more data. Usually it is not possible, but sometimes you may design your survey, design your own data, own experiment. So then you can achieve both given the if you carefully design your experiment. That is called experiment design, literally, and it is actually used in many like surveys and experiments. So let me briefly introduce how to handle that. So what we just saw is the insurance company wanted 99% confidence level and obtained a margin of error 1200, like nearly $1,300. But the insurance company was not satisfied. Like high confidence level is okay, but the margin is too large. It's too so it's not easy to make a decision based on this wide margin, right? So the company wants a more accurate estimation. So the new target is a margin smaller than $500 and confidence level no sacrifice at all, like 99%. Would like to maintain 99% accuracy, but the margin, I don't allow margin error more than $500. Then what can we do? We need to collect more data, and then we are going to calculate what is the minimum required sample size to achieve these both goals, to overcome the trade-off. Okay, now then it is about the margin of error. We would like to have margin of error smaller than 500, so we have to satisfy this inequality, right? Margin of error will be given this way, and this is smaller. We need this to be smaller than 500, right? This inequality. But at the same time, the confidence level should be 99%. That means this part is also fixed, right? Z alpha over 2 is fixed by the confidence level, which is 2.58. So this is fixed. This is fixed. Standard deviation is not what we can change, right? It is just nature of the data. So standard deviation is also fixed. We cannot change the cost of like the treatment, right? We are estimating the cost of the treatment. It's out of my control. Then the only thing we can change in this inequality is n, right? Sample size. If you collect more data, you can increase sample size, right? So that is our strategy. You can set and satisfy both goals if you increase the sample size. Satisfying like without changing alpha, you can satisfy this inequality. That's what I'm saying, right? How can we do that? The only unknown, we are going to solve this inequality for the sample size n, right? So move this term to the other side. So like this is what we have, like say 99% imply 2.58. Standard deviation is already 5,000. And then move these two terms. So we have this inequality. So it already shows that square root of the sample size must be at least this much, right? Now to remove the square root, we are going to square both sides, right? Square the right hand side will become n, and square this side we will get this number, right? Just simple algebra, use calculator. That means the sample size must be at least this much. But of course, the sample size should be a natural number. So the minimum sample size you need is 666. Okay. This is how we use like our confidence interval margin of error formula to design your survey and experiment, right? And it is the starting point of the survey, like survey design, experiment design. So the next is your exercise. Now I'd like to reduce the margin of error even more. The data are the same. You are given the same information, but now the margin of error must be smaller than 300. Then how much sample size do you need? You can do the same algebra. Okay, so do the algebra and stop the video if you need more time. And I'm going to show you the answer now. So again, remember 99% confidence level does not change. So that means this part does not change. Z alpha over 2, 2.58 does not change. But the inequality must be satisfied for 300. So this part changes. It is 2.58, but this must be 300. And standard deviation does not change, 5,000. You can handle the sample size, right? Then you get this inequality. And if you calculate the right-hand side, you get an integer. So 1849 is what you need for this inequality to be satisfied. Okay, so it shows how much you need to sample to obtain a certain level of accuracy and informativeness. It's pretty interesting, and in the next video, I will show you how this theory is applied to presidential election. So I will borrow the actual presidential election survey from the past, and will like show you how we apply what we just learned. Thank you for watching, and hope to see you soon. Bye.